Good morning and welcome back to a brand new chapter. This is chapter 3. In chapter 3, we are going to be looking at solving systems of equations, systems of inequalities, and stuff like that. This is a bit shorter of a chapter than the other ones, and it's closer to new stuff. It's stuff that you've probably already seen, but probably don't remember quite as well. First of all, so it's about solving systems of equations. What is a system of equations? A system of equations is at least two, so two or more equations, graphed on the same graph. That's really all a system of equations is. So, in this section, section 1, we are going to be using graphs and tables to solve systems of equations. Our learning targets for the day: I can solve systems of equations by using graphs and tables. Obvious based on the title. And I can classify systems of equations and determine the number of solutions. So that's a little bit of vocab with the classifications, and then number of solutions is a fairly important topic. So our first order of business is something an ordered pair, or is an ordered pair a solution to a system? And so if we have an ordered pair like -3, -5, is this a solution to this system of equations? Notice systems of equations generally have a curvy bracket to tell you that, hey, these are all both together. It's just two equations. And so is an ordered pair solution is a really, really useful skill to be able to do, because you're going to get ordered pairs and you're going to have to check them. So this is basically how you check your work. And to do that, we just need to plug the point into both equations, just separately. If it works for both, if it makes both of them true, then it is a solution. If at least one of them does not work, it's not a solution. And so let's plug it into the top one. 2 times y, well, y is -5, minus 6 times x, which is -3, equals 8. 2 times -5 is -10. -6, -3 is plus 18. So we have 10 plus 18, -10 plus 18 equals 8. -10 plus 18 is 8. Does 8 equal 8? Is that a true statement? Yes, it is. What would an example of a non-true statement be? 8 equals anything other than 8. 0 equals 1. Just anything that's not actually equal. All right, so it works for the top one. So we'll try the other one. If it did not work for the first one, we're done. We don't even need to try the other one. But it did, so let's plug it in. So 4 times y is -5, equals 8 times x, -3, plus 4. So 4 times -5 is -20. 8 times -3 is -24. -24 plus 4 is -20. So does that one work? Sure enough, it does. And so it works for both. -3, -5 is a solution to the system. For a question like this, you'd really just need to put yes or no. I made a full sentence. You don't actually have to do that. And so that's all you have to do. Plug it into both. Does it work? Well, that's great if we're given a point, but a lot of times we're not. We have to find the point. So today we're going to do that using a graph and a table. So starting with a system, x minus y equals -1, and 4x minus 2y equals 2, we are going to graph these two equations. And then we're going to use a table to check our answers. Solving with a graph and a table is basically guess and check. We're going to graph it, and that's going to give us a guess. The better, more accurate your graph is, the better your guess will be. I recommend graph paper. So we're going to graph this. And to do this, these equations are both set up to graph using intercepts. So let's find them. Let's use the top one. I'm going to make this one the red one. It'll be a red line. So intercepts. If y equals 0, x would equal -1. And if x equals 0, -y equals -1, so y would equal +1. We can graph those 2 points, connect it with a line, and there's the first line. The second line, we have 4x minus 2y equals 2. This one's blue. So if y equals 0, 4x equals 2, which means we divide by 4, x equals 1/2. And if x equals 0, negative 2y equals 2, divide by negative 2, y equals negative 1. We can graph those 2 points, connect the dots, and extend. And so we have the 2 graphs. So where would we be looking on the graph for the solution? What point would make both of these true? The intersection point. That is the point where both graphs are. It's where they both work. So when we're solving, we're finding the intersection point between the 2 graphs. And that'll be true next time when we solve algebraically as well. So where does it look like this point is? It looks like it's at 2, 3. Let's try that. We're going to plug in x equals 2 to the equations and solve for y. So in the first one, we have x minus y equals negative 1. So 2 minus y equals negative 1. We can subtract the 2, negative y equals negative 3, divide by negative 1 or multiply by negative 1, y equals 3. So the first one, the red one, we have y equals 3. And plug it into the other one. 4 times x, so 4 times 2, minus 2y equals 2. 4 times 2 is 8. We can subtract the 8 to get negative 2y equals negative 6. Divide by negative 2 to get y equals 3. And, hey look, the y values are the same. We have the point 2, 3 and 2, 3 for both of them. That means it works. 2, 3 is the solution. It is the intersection point. So now graphing, like solving by graphing, again, it gives us guess and check. Our graphs are pretty good. What if our graphs weren't so good? It might take us a couple guesses. What if instead of 2, 3, it was 2.1, 3.04? Are we going to find that by guess and check? Probably not. And so next time we'll learn how to do it algebraically. But right now they should all come out to be nice integer numbers, maybe a half in there every once in a while, but it shouldn't be much more than that. It should be a fairly obvious answer if you are graphing well. And so your guess and check shouldn't have to be all that much to make a table. So that's solving using a graph and table by hand. What about using a calculator? Sometimes it could be nice using a calculator, especially if the numbers are really big, where you're dealing with hundreds. It might be a nice integer number, but can you tell if it's 215 or 217? Possibly not. So the graphing calculator will definitely help there. So let's look at how we do this. We have a new system, 3y plus 6x equals 3, and x minus y equals negative 7. We're going to get out our graphing calculator. I recommend if you have a graphing calculator, follow along. Like actually do it. And so when we plug stuff into a graphing calculator, we can't graph using intercepts. Graphing calculators don't do that. We have to make it y equals. So we have to solve for y. I'm going to take the first equation. I'm going to make it blue. And we'll see y in just a minute. And we're going to solve for y. So the first thing is we have to subtract the 6x. So 3y equals negative 6x plus 3. Then divide by 3. Y equals negative 2x plus 1. Notice when I divided by 3, I divided everything by 3, not just that first one. It's one of the common mistakes. Make sure you divide the whole side. And so that's the first one. The second one, x minus y equals negative 7. So we subtract the x over. Negative y equals negative x minus 7. Multiply by negative 1. Again, we have to multiply everything by negative 1 to get y equals x plus 7. And so now we can work on graphing this. To graph it, we're going to go to the y equals button. And then we have two equations. We're going to put it in the first one. The negative is down here on the bottom. This is minus. I know they mean the same thing, but the way the calculator is programmed, it's different. The variable button was right up here. So we've got one plugged in, got the other. While it's plugging in, notice the colors. The first one's going to be blue, second one's red. That's why I made them blue and red in this order. So we got them plugged in. We can hit the graph button. And oh my goodness, my zoom is way off because I was graphing something different. That's okay. Go to the zoom button. And then if you do zoom standard, on this one it's number 6. That gets it to a basic zoom window. There's the first one and the second one. And there's our intersection point. And it looks like it's about x equals 2. So we're going to go to the table, which is second graph. And it's going to pull up the table. And then we want to go to where x equals negative 2. So we have to scroll up. And look, negative 2 and 5. The y values are the same, which means that that is our intersection point. And so that's the solution. The solution is negative 2, comma 5. And we got that by using a graph and table. We got both lines to be y equals. We plugged them into the graph, and we graphed. We found where the x value of the intersection point was, and we looked on the table for the verification of the y value. So that can come in very, very handy when doing these. The last thing we have is classifying systems. So there are a few things that two lines can do when you graph them on the same coordinate plane. The first is they can intersect. That's what we've been working on. That's kind of the normal. That's the general thing that tends to happen. And when they intersect, they look like that. These are called consistent independent. It's a consistent independent system. And how many times do these two lines cross? One time. So it has one solution. There are a couple other things that two lines can do. What's one of them? How many of you are thinking, ooh, parallel lines? Yes, that's one of the things that can happen. Parallel lines look like that. And as we know about parallel lines, they have the same slope. They also never intersect. These are called inconsistent. It's inconsistent because there is no solution. They don't intersect at all. So when they do intersect, when there's a solution, it's consistent. When there's no solution, it's inconsistent. All right, there's another thing that can happen with the lines. Can you think about what it is? Some of you already have it in your head. How about coinciding lines? No, what does that mean? Coinciding? Is it heads or tails? No, coinciding. And that means it's the same line. You can't see it, but there's actually a red line underneath this blue line. But it's the same line. And this is consistent and dependent. It's consistent because there is a solution. In fact, there's infinitely many solutions. Every point along this line will be a solution. Now, that's not all real numbers. Because all real numbers, like we have our solutions in ordered pair, would have to be all real numbers, comma, all real numbers. That means the whole plane. It's just this line, so it's just infinitely many solutions. This happens when both the slope and the y-intercept are the same. Parallel lines happen when the slope is the same, but the y-intercept is different. And intersecting lines happen when the slope is different. The y-intercept could be the same, could be different, doesn't matter. But the slope is different. They will intersect. And so that would be solving by graphing. We have some vocab here with the names. The most important thing about these is knowing that these three things are possibilities and knowing how many solutions. In the long run, the consistent, inconsistent won't be that important. Will it be on the homework? Yes. Will it be on the chapter test? Possibly. But like really in the grand scheme of things, that's not as important as the rest of it. So this is the first section. Make sure that you follow the directions on what you have to do next, and I will see you next time. Until then, happy mathing.